When you think about gears, what comes to mind? Do you start thinking about all kinds of complex machines that we have invented over time? Maybe you think about car transmissions. Or maybe you think about factories that utilize gears, or even the intricacies of a well-made watch. Maybe even a bicycle. When we think about gears, we think of ways that we as humans have engineered and used ingenuity to make something run with precision and alignment. Gears take a lot of work, a lot of adjustments, and a lot of precision, a lot of design. But when we look at gears, what we see is human invention and design, right? Well, what if there was a little bug that also used gears? How would something that is so complex and so designed and so purposeful find its way in a bug? Let's take a look at the leafhopper today. Back in 2013, Cambridge professors Malcolm Burrows and Gregory Sutton began researching the tiny little bug called the leafhopper. Now, Malcolm Burrows had seen these little leafhoppers in his garden growing up, but when they really began to study one particular leafhopper, they found it had gears. Now, leafhopper is just a generalization of a bunch of insects. It has about 20,000 different varieties, but this one was the only one that they ever found that had gears. And today it is hailed, this particular leafhopper is hailed as being the only insect to have ever used gears or ever found to have gears in nature. But before we take a look at these gears, let's take a look at the little bug itself. This leafhopper is very small. It's only about 2 millimeters long, and yet it has a very, very powerful jump. It will go from a stopping position, a still position, to 8 miles an hour in roughly 2 milliseconds. And that may not sound like much, but it's quite a fast jump. Just by way of comparison, when we blink, it takes roughly 100 to 400 milliseconds. Now again, the bug is jumping in 2 milliseconds. So I guess if you've really been working those eyelids, maybe you'll blink in 100 milliseconds. Some of us maybe are slow blinkers and we'll blink. It'll take 400 milliseconds to accomplish the blink. You know, we even use an expression of speed. We say in a blink of an eye, meaning very fast. Well, if that takes 100 milliseconds, the leafhopper is jumping in 2 milliseconds. So it's a very fast jump. When the leafhopper goes from 0 to 8 miles an hour in just 2 milliseconds, it's accelerating with a force of about 500 to 700 Gs every time it jumps. Now, if you remember last week when we were talking about the woodpecker, we know that G-force is something that can really do a lot of damage to us as humans. If you remember, just 10 Gs over a solid minute can pull the blood out of our brain, and it can cause us to die. And even a couple hundred Gs can do incredible damage to us. For the leafhopper, no problem at all, 500 to 700 Gs every time it jumps. The problem is in the fact that it's jumping in just 2 milliseconds. Because if you think about this, if it's leaving the ground in 2 milliseconds, that means that if one leg pushes, and this leg is 2 milliseconds behind, it means it's already in the air before the other leg has jumped. In fact, as Malcolm Burrows explains, by the time the insect has sent a signal from its legs to its brain and back again, roughly 5 or 6 milliseconds, the launch has long since happened. So what this means is even before its brain has processed that it's jumping, it's already off the ground. So it doesn't have the brain capacity to synchronize the jump or to really think about both legs. It's pushing so fast, its brain doesn't even, hasn't even registered that it's jump. So it has to be in sync. Now, if you're not in sync, if you're not pushing at the same time, that's going to cause you to jump off into a direction that you were not trying to jump. And so if it's sent off in the wrong direction, where could that little bug end up? Well, it could end up in a body of water and maybe drowned or be eaten by a fish. It could jump off of a high surface and maybe sustain damage because it is now falling from a great height. Or it, instead of jumping away from the predator, maybe it jumps towards the predator right in his mouth and gets eaten. It has to synchronize the jump in one way or another. And so how is it going to do this? Gears are the way that this little bug is doing it. Let's take a look at the jump real quick and just see how fast these type of jumps are going. When we take a look at this little leafhopper right here, it begins powering up and it's gone. Wow, I mean, it's so fast, the camera doesn't even really have the chance to keep up. Let's slow it down as much as we can here and see what's happening. So again, it's starting to curl up to jump, and it just disappears. The camera shutter cannot keep up with how fast. It just kind of looks like it just disintegrates off the screen because the camera can't keep up with just how fast this little bug is jumping. Well, how do other leafhoppers do this? Because again, when we talk about leafhoppers, we're talking about 20,000 different types of insects. Well, most other leafhoppers use friction. They'll use the feel of their legs rubbing together to time the jump with great precision. And what's interesting is that these other leafhoppers are actually better jumpers and they're jumping more quickly. And so why would it use gears, a much more complex way of jumping, to do this jump? It doesn't make sense when all of the others are just using friction. So let's talk about these gears. In order to form these gears at all, it's actually using its exoskeleton. So the exoskeleton is the outer kind of shell of insects. And for this particular leafhopper, it will use gears in its hind legs. And when we really begin to look at these gears, we see that they are very, very well designed here. They look just like any other cog or wheel that we would see in even our own type of machinery, where the edges of the teeth are kind of rounded off so they can make their way into each other. We're seeing that they are the proper depth, and they have even the channels on the inside are perfect so that it goes exactly like it's designed. We also see that the teeth are going to fall in line with each other, and they're not going to hit on each other and break or cause other damage to the bug. They just are perfect in the way that they're designed. And these gears are working so well with so much precision that it's causing these legs to launch within a minuscule 1/300,000th of a second of each other. So, I mean, virtually at the exact same time, these gears are allowing the bug to push off at the same time. Now, here's where it gets really odd, because this leafhopper only uses gears in its juvenile form, in its kid form. What will happen is these gears are maybe almost like a training wheel for this bug. So when it's first kind of born, it will have these gears. It will begin using these gears, and then it will shed its exoskeleton as it grows. And then once it reaches adulthood, it stops using the gears. It doesn't need them anymore, apparently, because at that point it begins using friction, just like all of these other leafhoppers. Well, wait a minute. If it didn't need them to begin with, then why would it start with them? That's odd. When we're looking at these gears, it screams of a designer to me. This is an animal that blows my mind, because when we look at something that is so clearly made and intricately designed, how does something like that get inside of a little bug? See, and it doesn't even need these gears. So why does it have them at all? The other leafhoppers don't use it. It doesn't even use it later on in its life. So why have them at all? It doesn't really make much sense. Why would it go through such a complex evolutionary process when you don't even need to, and you're not even going to use it for your entire life when all of these others aren't even using it? I mean, why would you go through the process of something so complicated when you could use something so simple like friction? And how much trial and error would it take to get these gears just right? I mean, how does it even know of the concept of designing a gear? Like, where does that come from? You don't just accidentally have these mechanisms that perfectly align and are mirror images of each other, except that they fold within each other like this. That doesn't just happen by accident. And how would you know that this concept can even be a solution for this to begin with? Now, what happens when the teeth are out of alignment? You break a tooth, or maybe it causes damage to the bug's legs and it can't jump anymore. Or what if the teeth were different sizes in the evolutionary process? What happens if the cogs aren't functioning? Maybe one's in front of the other, or maybe they're too far apart, or the millions of different varieties that these different little cogs could have. How many different tries would it take over how many different lifetimes to finally get this right? See, it doesn't really make much sense that over millions and millions of years that it would finally develop the perfect cogwheel, all the while destroying itself or killing itself or crippling itself and making it to where it can't jump, just to form these type of gears. Not to mention that, once again, none of the others are using gears. Before Malcolm Burrows and Gregory Sutton were studying the leafhopper, science long touted gears as being strictly a man-made invention. That this was the first time that gears had ever been found in nature. And according to scientists, there has never been any other animal, not one alive today, there's not an example in the fossil record, there's no other known animal that has ever used gears. So, this is why it's baffling when we see this type of statement from the researchers who even found it themselves. They said, these gears are not designed, they are evolved. Okay, now hold on just a minute. Never seen an animal like this. Never seen any animal in the animal kingdom that has gears. Okay? Never found it in the fossil records. Not one time. Never. We've never seen it in the fossil record. Okay? And there's no example, there's no information, there's literally nothing except for this bug that has ever been seen to utilize gears. Okay? So then what evidence is there that it evolved? See, there is no evidence. There is no proof, there's no information to say that it's evolved, and this is one of the things that I have, one of the problems that I have with that type of statement and overall with evolution. Because the bottom line is, they are going on blind faith, particularly in this example, to still claim that the leafhopper evolved when there's literally no evidence that it did. See, this isn't a fair playing field. See, this isn't a fair playing field. This is a field of opinion and bias and perhaps even dishonesty, to ignore the facts and ignore the good questions that we're asking. This isn't even science. What this is are assumptions and opinions. In science, if something is not observable, repeatable, or measurable, science would call that garbage. Well, there is no observable, repeatable, or measurable aspect to the gears in the leafhopper. You can't call it evolved. When I look at the leafhopper, what I see is something that has to have design behind it. To have the teeth that perfectly fall in line with each other, to be rounded on the edges so that they are able to clear, making their way into the channel. What I see is intelligence and ingenuity. What I see is that this came from the product of a creator, and that it's a creation from the God that we serve. When I look at the leafhopper, I see just one more cog in the intricate wheel of God's design in this world. What I see is evidence of a creator. In Psalm 104, the psalmist says, "O Lord, how many are your works? In wisdom you have made them all. The earth is full of your possessions. There is the sea, great and broad, in which are swarms without number, animals both great and small." Our God is responsible for some of the most amazing creatures on the face of the planet. Some big and elaborate, some tiny, like the leafhopper. But when we get down into the details, the answer is always the same. We see evidence of our God. Let's go ahead and look at one more animal, and that is the bat. Now, in bats, there are about 1,200 different varieties of bat. There are 1,200 known species. About 3/4 of those eat insects. Now, of course, they are going to range in their various abilities and features, but a bat is pretty amazing, and they really help out our environment quite a bit. Matter of fact, bats will usually eat about 1/3 of their body weight in insects every night, which is equivalent to about, which is hundreds of insects in just a few hours. The little brown bat can eat up to about 1,000 mosquitoes in an hour. Man, thank you for that. I don't want any of those mosquitoes. It's a good thing that they're eating them up. If bats became extinct, the insect population would go out of control, and that would be really bad for our world. In fact, there are about 30 million Mexican free-tailed bats in a cave known as the Bracken Cave in Texas. And these bats eat about 250 tons every night in the summer. First of all, why does Texas have that many insects? Second of all, thank you, Mexican free-tailed bats, for taking care of a bunch of them. But not only do these bats play a significant role in the insect control, but they also are playing a significant role even in pollination. And so obviously if bats didn't exist, our world would be quite a bit different. So we're thankful for bats. But not only are they helpful to our world, but they are a package of some really, really cool features. Let's take a look at some of these. When you think of a bat, what do you think of? Well, you probably either are thinking of their wings or the fact that they hang upside down. Well, when we talk about their feet and how they're able to hang upside down, they're pretty amazing. They actually work opposite of most mammals, and particularly us. So what we have to do is we have to use our muscles to contract our hands to hold on to something. For the bat, though, they work opposite. See, when we relax, our hands open, or they relax. We go from a clench position, we relax, and then they open. Bats are opposite. When they relax, it clamps down. And so hanging from the underneath side of a tree, no problem at all, because they're actually in a relaxed position. To actually let go of the tree, they have to contract their muscles to open up their feet and to be able to let go. Not only that, but their toes work kind of like a slip knot. And what I mean by that is the more pressure, the more weight that it has hanging on the toes, the more locked down that they become. So when it hangs, its toes actually lock down tighter, and it has no problem at all hanging from the underneath side of whatever it wants to hang underneath from. Also, its circulatory system is perfectly designed for this. It doesn't get lightheaded, it doesn't get dizzy. Even the little brown bat can hang upside down for 7 months at a time while hibernating. No problem, no issues at all. It's perfectly designed to hang upside down. However, there's kind of a foundational question here. Why? Why would the bat hang upside down from underneath a tree branch, for example? Why would it do this to begin with? Well, since it is a mammal, It doesn't have the hollow bones and the structure built like birds do to be able to fly. Most bats actually can't fly from the ground. So they actually have to drop in the air a few feet and get their wings flapping in order to actually get airborne. And so if you were to take some species of bat and just put them on the ground, they wouldn't be able to fly. They need to be able to drop down from something, and hanging upside down from underneath a tree branch or something like that is the perfect position for it to be able to drop, start flapping, fly on his way to get a delicious little buggy who's flying around out there. But the other identifying feature are their wings. Now, the wings of a bat are unlike most other wings in all of the animal kingdom. For one thing, it doesn't have feathers and things like that. What it actually has is almost finger-like structures. Even the bones are flat and flexible, and then a membrane is growing across or spanning across these fingers, if you will. And so it's able to take the unique shape that we see from, symbols like Batman. And if you just look at the symbol of a bat, it's very recognizable because of how unique its wing is. And this skin, or the membrane going across going across the wings, is very adaptable. If it gets a tear or something like that, it grows and heals itself because it kind of is dependent on flying. And so it's got to have a way to keep itself up in the air. And because of the design of the wing, and since it is able to, basically utilize them like fingers, it can change the shape of its wing. And so if it needs to go faster, it'll change its shape, or if it's a windy day, it'll change the shape of the wing to accommodate for what it needs to do to be able to fly efficiently. And they're very, very skilled flyers, sometimes even better than birds. And some bats can even fly at upwards of 60 miles an hour. So very good flyers, very efficient. But perhaps most amazing of all is that on the surface of the wing are little bumps that have a hair growing through the center of it. Now, these bumps are incredibly sensitive. They're about as sensitive as our fingertips. And what they utilize these bumps for is a couple of different things. They'll actually feel the different air conditions, whether it be windy or rainy or whatever it might be, and they will change their wing shape based upon the information that they get from their wings. Also, when it's closing in on a bug, it will sometimes wrap around the bug and kind of use the feeling of its wings to bring the bug in and eat that delicious little bug. And so, very sensitive, very adaptable, very good flyers. Now, the way that bats reproduce is also really interesting. They're mammals, and so they will have breeding seasons just like many different animals. But unlike other animals, the female bats can actually control when they have their young. And so there are some species that can even can store the sperm for a later time, or even delay the implanting of the egg until there's plenty of fruit or there are more plentiful insects flying around. And so if the mating occurred in the fall, then the female can actually delay the process of having its young until the spring, when there is more food and it's better conditions. Also, bats will only have one young at a time, so that it gives the bat the best chance at survival. So very interesting that they can control things like that. But of course, the most amazing feature of all with bats is their echolocation. Their ability to see, if you will, with sound. Now, contrary to popular belief, a lot of bats have great eyesight. Matter of fact, they have tremendous eyesight around dusk and dawn, like a lot of different animals. But there are some that do not. No matter, even in the dark, flying at night, tracking down a little bug is something that can be very, very hard. So it needs this echolocation to find the bugs and to get its meal for that evening. To be able to make a noise and to pinpoint on an insect because of an echo off of that insect, I mean, that'd be such a small echo. It's such a small detail. How is it able to do this? It's very, very amazing. And so when we're looking at its hearing, they have very, very sensitive ears. So for example, There are some bats that eat frogs, and those bats that eat frogs are able to tell which frogs are poisonous and which ones are not, just based on the variations of the frog's noises and mating calls and everything like that. The African heart-nosed bat's ears are so sensitive that it can actually hear the footsteps of a beetle walking on the sand. And so their hearing is, of course, just finely attuned to all of the different noises that are going on around them. And so they are perfectly designed to fly with sound. The noises that bats make is incredibly loud. Most bats are producing sounds upwards of 100 to 130 decibels. The equivalent to this type of sounds are the sounds made by jet engines and machine guns. And thankfully, the bat noises a lot of times are so high pitched we as humans cannot hear them, but they're very, very loud. There have even been times where their noises have been measured in large groups when they're in caves or in a tree or wherever that they are, and their noise levels are reaching upwards of 140 decibels. Now, that's equivalent to the sounds and the noise that would be found on an aircraft carrier, with like fighter jets launching off of the deck and all of the machinery and all of the noise. If you've ever seen pictures of that, the personnel that are working on top of the deck all have hearing protection because it is just so loud. Well, with that type of volume, why aren't bats deaf? You see, they're even enduring 140 decibels for hours at a time. How in the world are they still able to hear? When we think about hearing damage, this occurs when there are loud noises for too long. And so sometimes if it's a very loud noise, even for a short amount of time, it can damage those sensory cells in our ears. Or if it's maybe even 90 decibels, but it's for a longer period of time, that too can damage those hearing or those sensory cells and cause hearing damage. And so we know that bats are producing sounds of 100 to 130 decibels. And so that's very loud for its ears, even the sound that it's producing. And when it's closing in on a bug, sometimes it will begin to do kind of a rapid fire noise at those volumes to close in on the bug, find out where he is, and be able to eat him. And so how is it that it's not damaging even its own ears? Well, inside of the bat's ear is actually a little muscle that's attached to the bone. And so when it goes to produce a sound, it flexes that muscle and the bones pull apart, and it essentially plugs its own ears. And so that the noise doesn't transfer through the ear into the brain, and it's no problem at all. So it has the ability to dampen the sound all by itself, and it will do that when it produces a sound. But beyond even this, bats are extremely resilient to hearing loss. There was a study that was conducted at Brown University back in 2016, where they were studying just this and trying to figure out what kind of damage do bats sustain when they are undergoing loud noises like the 140 decibels inside of a cave. What they did first was train the bats to come wherever that they wanted by the producing of a sound. And so they were able to determine by measuring the volume if the bat heard that, because it would come in and get the tasty little treat. Once they got that down, they began subjecting these bats. They had two groups of bats, the bats that were the test case and the bats that were the control, the ones that would not be subjected to loud sounds. And so they took these bats and they subjected them to very loud sounds for an extended period of time. And then they measured, are they able to hear? And they would measure it right away, and then they would measure it at 20 minutes, and then they would measure it at 24 hours later on to see if their hearing had improved. Let's pause for just a minute and talk about how you measure hearing loss. It's measured by decibels and how many decibels of sensitivity have been lost. So for example, if you go to a loud concert and then afterwards, people are trying to talk to you and you just can't hear them, what that means is that you have lost sensitivity and that people have to be louder. They have to increase the volume in order for you to hear. And so if you've lost 15 decibels, that means that a person that would talk to you normally has to increase their volume by 15 decibels in order for you to hear. And then we can also lose hearing in high frequencies or low frequencies. And so a lot of times older folks who have lost some of their decibel sensitivity, and they also are maybe losing the ability to hear some of the higher pitches, when they get hearing aids, they'll start hearing birds again. Because they're a higher pitch, a higher frequency, and it's kind of a soft ambient sound. And so they'll hear birds again when maybe they weren't able to hear it because of their hearing damage. Okay, so for these bats, when they went to measure the sensitivity loss that they had, there was only one bat that had a 5 decibel sensitivity loss. All the others had an average of a 0.6 decibel loss. Virtually nothing. And then after 24 hours, their sensitivity actually increased by 1.7 decibels. And so it was as if almost it improved their hearing. And what that meant is that the bat is very, very resilient to hearing loss or hearing damage, and that it is perfectly designed to undergo loud noises for its entire life without any problem at all. Now, here's what's really interesting. The way that we as humans measure hearing loss, the scale starts at a 6 decibel loss. So that's when we begin to say, okay, there has been some hearing damage that has occurred because your sensitivity has been lost by 6 decibels. Well, not even one bat had a 6 decibel loss. The max was 5, and it even improved just a few minutes later. So we know that it's producing extremely loud noises. We know that its hearing is very, very sensitive, but it doesn't sustain hearing damage easily at all. But how is its brain even able to process this information? This is where we start getting into territories that are so complex. Because what we're talking about is that this bat is able to make a noise, and then when that noise reflects back, it filters through the ear catches it and filters it into the brain. And that brain, in just, a fraction of a second, notices that there's a bug here and there and there. And oh, there's a tree here and there's leaves on the ground. And oh, there's a beetle that is, walking along the sand. And in just a fraction of a second, how is it able to process all that information so quickly and so efficiently? Matter of fact, scientists will say that it's processing information at a 99% accuracy. I mean, it is unbelievably good at using sound to figure out everything that's around it. To give an example of just how fine-tuned and sensitive a bat's echolocation is, there are some bats that go for minnows, that fish. And when they go out fishing, they're able to detect a minnow's fin, which is as fine as a human hair, that's sticking just 2 millimeters out of the water. And so they are able to detect the little fin of a minnow down there in the water and go down and grab that little minnow and have dinner that night. One other question that has kind of boggled my mind is, why doesn't it get confused by all of the other bats? See, its ability to travel and maneuver is based on sound. Well, if you're in a cave with a ton of other bats making loud noises, how are you able to distinguish that and function at all? Or other bats flying around, how are you able to do that? Well, a couple of ways that they're able to do that. One is they'll change their frequency. They'll make it a little higher, a little lower, based upon the other bats that are around them. And they'll kind of find a butter zone that no other bat is using, and it'll be able to fly around using that frequency, no problem at all. It also seems to be able to filter out some of the noise that's coming and kind of focus in on its own voice. We even kind of do this as humans, particularly moms. If you've ever been in a crowd where a mom goes, "Oh, my baby is crying," or "Oh, I heard my kid say such and such," and it's like, man, I don't know how you heard that. There's so much noise that's going around. A mom's brain has been designed to almost to be able to filter out other ambient noise and focus in on the sounds of their own child. And in a similar way, the bat is kind of doing that by focusing in on its own noise so that it can maneuver around, fly around, find bugs, no problem at all. Does it perfectly. You know, they really missed out on this one with Batman. Because Batman does not have any of these amazing features. How cool would it have been if Batman had the ability to just with a single sound know everything that was happening in a room, and be able to navigate through the dark cities and the dark street corners just by being able to make noise. They kind of missed out. They call him Batman just because he's got kind of the wings, but didn't have all the cool features. When we think about how something like this can evolve, again, it just boggles my mind. Because this is the only mammal that's able to fly. Yeah, you have like, quote, flying squirrels, but they're really gliding, they're not flying. Because mammals, by and large, don't fly. But if this was an evolutionary process, why aren't there more animals that fly? I mean, how many different predators could utilize the ability to fly? Can you imagine a fox being able to fly, silently swooping in on an unsuspecting little rabbit or something like that? Or maybe even some bigger animals that were able to fly. I mean, it could be extremely useful, or even glide. There are so many different uses to the ability to fly, and yet this is the only mammal that can do it. How would the bat develop the ability to know that it needed to be elevated? Also, how would he decide that he needed specialized feet to be able to grip? And how would it, over a long period of time, change from flexing to let go as opposed to flexing to grip? Because if you're in the in-between stage, you're either having to flex to let go or flex to grip, which means that there would be an in-between stage perhaps when he couldn't do either. And so how would he develop this ability? How would those in-between stages look? And would he be able to function at all? And why would he even choose to fly at all when no other mammals do? How would he even know that flight is possible? Instead of just crawling around on the ground and getting bugs and different grubs like all of the other mammals do, why would he choose this? And how, again, would he know how to do that? And how would he, decide to start elongating his fingers and flattening the bones of his fingers and begin growing a membrane? How would he know all of the specifications of flight? How would he know how much propulsion that he would need to get airborne? And all of these various features, it's so complex. And it's so amazing and so mind-boggling to think that this is something that could have just happened over millions and millions of years, because what we're talking about is so much trial and error. We're talking about so many different varieties that it would leave the bat crippled or in an in-between stage where it would not be able to function anywhere even close to the way that it does today, not to mention all of the echolocation. How does an animal develop the ability to see using sound? How would it develop the ears to be able to withstand all of that noise? Because for a long time it won't have that ability, because it's developing it. How would it develop the muscle in the inner ear to be able to pull apart the bones and to be able to plug its own ears? How would it develop something like that? And if it didn't have that, would it not go deaf? And if it's not resilient to sound, would it also not go deaf and then not be able to function using all of this? Also, how would its brain get to the point to where it was able to diagnose the sound with 99% precision? I mean, what would the precision start out? 50? And so instead of running away from a tree, it runs into a tree. There are so many very, very complex features that are occurring here, from its feet to its ears to its brain to the ability to fly. All of it has to be fully functioning and perfect. And yet it poses so many questions and that we just do not have the answers to on how something like this could truly evolve and develop these features over time when we don't see the evidence of it. We don't see it in the fossil record. All we see are fully formed, perfect, and amazing bats. The Bible claims in Genesis 1, verse 21, that God created every winged bird after its kind, and God saw that it was good. Certainly bats would be included in that. That God designed the bat to be exactly the way that it is. In Psalm 104:24, it states, "O Lord, how many are your works? In wisdom you have made them all. The earth is full of your possessions. The amount of wisdom and knowledge and design that's contained in the bat is mind-boggling. Even just trying to find the information on how a bat is able to not lose its hearing is so few and far between, because there's so much about the bat that we don't even understand today, that scientists are continuing to study and look into because it's so complex, and that we just don't have the information. And yet for God, in His infinite wisdom and knowledge, He can create something so incredible and so amazing. And it blows my mind to see God's creatures and to see all the things that they can do. It proclaims the God that we serve. It tells us that He exists, and He is one that deserves our worship and our praise.